Dzień dobry and dziękuję. As a person of Polish heritage, I'm very proud to be presenting to you today. I'm sorry that I can't be in Warsaw. I'm currently located in Amsterdam, the Netherlands, and I look forward to a future opportunity to present in person. Today, I'll be presenting to you about approaches to real-time analytics for cybersecurity. This topic is very close to my heart. I've been active as a consultant and expert in the field of cybersecurity analytics for the past 7 years at Deloitte, SAS Institute, and most recently through my own firm, SARC7. I've also been an active researcher for the past decade on the topic of cybersecurity data science. I'll be defending my dissertation at Nyenrode University in the Netherlands in December, and my book will be coming out, published via Springer in 2021. So today's presentation will be deriving insights from both my professional work and my academic research. Today, I'll give you an overview of some of the challenges associated with real-time analytics for cybersecurity. I'll also give you a perspective on key solutions, and I'll be orienting these solutions towards three major areas from the management of information systems discipline, which is to address the technical, process or methodological, and organizational aspects of real-time solutions for cybersecurity. So to get started, I'd like to give a brief overview of the domain of cybersecurity analytics. First of all, I don't think we need to spend much time to recognize that there's a great amount of fear, uncertainty, and doubt concerning how we can protect the proliferating internet infrastructure that is dominating the modern world. One thing we can say is that the traditional paradigm of cybersecurity, which is a castle and moat protection approach, is increasingly obsolete, which is that the idea of erecting hard walls, firewalls, and strong protection on the border of a network is increasingly invalidated. And this is largely because the vulnerabilities of the network are increasingly inside the network, and there's many ways that new technologies are creating tunnels and vulnerabilities that puncture through the traditional walls that have been used for protecting cybersecurity infrastructure. This is to say that essentially the internet has connections both inside the network that can potentially tunnel through firewalls, but potentially can bypass them, which is that we all increasingly carry around mobile devices with often autonomous connections that can then also provide entries into allied networks that we're connecting to. So the challenges are increasingly multidimensional and complex. The ways that we can address protecting infrastructure now has to encompass not only protecting endpoints, but protecting the servers, also addressing cloud systems and access, and also monitoring traffic, both on networks and with the internet. So metaphorically, if we were to think of the modern challenge as a airport security problem, we have masses of people, many millions of people coming through every second in some cases that need to be checked efficiently. People, of course, are using networks to do important work, and we need to, as much as possible, make that process efficient. Indeed, there's many unusual exceptions associated with people who are using the internet in unusual ways, but may be connected to their role or their job. And it's important that we allow them to continue to do that important work while still protecting the networks and infrastructure from people who may be trying to circumvent security. So indeed, data analytics is one of the great hopes of addressing the shortfalls of the castle and moat paradigm, which is to use data analysis to find these hidden threats and to disassociate real uses of the internet from anomalous threats that are showing up on the network. And so cybersecurity data science offers a set of methods for addressing some of the challenges of big data analytics for cybersecurity. And so these include data that's coming in at great volume and speed, data sources that are disconnected and fragmented, often lacking a context for users and devices and their situation and interaction with the network. Limited security staff who can only follow up on so many alerts and incidents per day, and then multiple systems that are creating many alerts in typical security operations centers and environments. So cybersecurity data science as an emerging discipline uh, addresses a lot of these challenges by proposing to use data science methods to address cybersecurity challenges. So this includes ways of improving data engineering for cybersecurity, reducing data volumes to produce focused discovery and detection, which creates targeted alerts, to set up automated models, and to optimize resources, to optimize the time and attention of cybersecurity defenders. This brings us to our first major challenge in preparing for real-time data analytics for cybersecurity, which is the technology, namely data engineering challenges. Prior to explaining some of these challenges, I'll just briefly cover some of the main data sources associated with cybersecurity analytics. These include log files, network flow data, and data coming out of identity and access management systems, as well as physical security systems, endpoint monitoring, packet capture, and SIEMs. Now, the discussion about cybersecurity data can be very abstract. So, in order to make it concrete, I will use the metaphor of Legos, which is we can think of a discrete piece of cybersecurity data as something like an IP address, a timestamp, or user ID, or a destination port, and that would be a single piece or element of data. Now, a data source such as a log file has several pieces of these data in composite. And when we want to assemble a picture of user or device behavior, we combine several sources together, which give us an aggregate picture of the traffic and activities that are going on a network. And from these, using analytics, we can build up things like a user behavioral profile to understand how users are interacting with the network and internet over time. Now, this creates, of course, a massive amount of data and a large amount of different types of data that are coming at a very high speed and in irregular patterns as well. So over time, we have ups and downs of huge amounts of data that are streaming that need to be collected and managed. In aggregate, if we think about the Legos, this amounts to a huge pile of Legos being dumped every second that need to be sorted and managed. The three key challenges are those associated with big data, which are very large volumes of data, sometimes terabytes or petabytes per day for some organization, the high speed that this data is coming in, and the many different sources of data that need to be aggregated, transformed, and integrated. So we can think of three main challenges, including processing volume, preparing and doing and conducting real-time analytics, and structuring and integrating varieties of different types of data. When we dig a bit deeper into the engineering challenges that are associated, there are problems of scalability, which is scaling the systems for real-time data, developing approaches for fault tolerance, which is finding ways to deal with errors that can occur as these large amounts of data come in, creating models and having those models respond to both real-time data and in some cases also batch data in the same context. and also dealing with issues of timing, which is sometimes data comes in late and needs to be rationalized. So from this large pile of Legos, we can certainly take an approach of using a number of the big data technologies that have come out over the last decade, principally, of course, the Apache Hadoop ecosystem and a number of associated tools that allow us to rationalize, manage, and store and transform data at large volumes and speeds. And for some of the best practices associated with big data management, I can refer you to a very fine white paper on this topic about governing and managing big data. And so there's a number of different elements towards managing big data and data lake architectures, which include cleaning and dealing with issues of data quality, as well as governance and securing that data. Ultimately, what we'd like to achieve, again, in the Lego context, is to have a very organized understanding of the types of data we're dealing with and an ability to access it and integrate it at will. Now, essentially, what we're attempting to do is to take unstructured, chaotic, high-speed data and to integrate it and transform it to address issues of quality and issues of validation at very high speeds in order to bring it forth so that it can be analyzed very quickly. And for a wonderful case study on how this is done, I would like to refer you to a written up case study, also available as a presentation on YouTube, concerning what was done for the New York City Cyber Command Department in order to protect New York City's cyber infrastructure using the Google Cloud platform. I think this is very instructive because some of the large tech companies, Google in particular, have created mechanisms for managing large amounts of data at volume and velocity for their own products and for their own services, which they've now made available in terms of creating platforms available for others to use. So the Google Cloud Platform benefits from over 15 years of research and development that Google's done to improve its own products and services that are now available to enterprise customers that wish to also manage large sets of data at scale and at speed, such as for the problem of cybersecurity real-time analytics. So some of these problems, I think, are beyond the scope of what we can cover today, but just to give you an example, there's an issue of processing different data pipelines that are coming in at great speed and data that needs to be collected and aggregated at great speed. And there's a problem of latency. Some data will come in before other types of data. And so there needs to be an ability at a very high speed to match data that may be coming in at uneven timestamps and to integrate it to make very quick decisions about data that may be coming in late due to latency. There may be an older event that comes in before a newer event, and those need to be rationalized using timestamps and a number of mechanisms. So Google Cloud Platform has a wide variety of tools to address all of these engineering problems, including real-time transformations, doing event time windowing, which is that as different events come in through time windows, they need to be matched up and analyzed according to the recency of the events. There are issues really regarding lateness and validity of the data. So there needs to be a strong validation of the data very quickly. And as I mentioned previously, there needs to be a way to handle data coming in late. And then there needs to be a way to accumulate that data and present it quickly, for instance, to cybersecurity operators or to machine learning models, as the case may be, at a very rapid speed, again, and also at great scale. So These challenges, the data engineering challenges, have been, there's been major advances made over the last decade because of the large technology firms, Google as being a very great example. Um, However, this then does not get us off the hook, which is in order to prepare for real-time cybersecurity analytics, we also need to conduct uh, data science in order to understand what's going on in this data to create models for detection, for alerting, and for remediation. In essence, when we'd like to process cybersecurity data in order to identify and resolve cybersecurity incidents, it's a staged process in which we first ingest and integrate and transform data at very large scales and at speed. That data then needs to be enriched with some context about what's going on. Who are the users? What are the devices? What is the context of the usage? And is it unusual or is it expected? From there, analytics can be conducted, both statistical analysis and machine learning, unsupervised and supervised machine learning, to provide contextual alerts to disassociate unexpected but normal events from events that look to be a genuine security incident. And then to present alerts and incidents and oversight to cybersecurity investigators, analysts, and managers. The difficult thing here is to develop an understanding of context, and that's where data science in particular provides value, which is there are genuine questions about what do we mean when we say a cybersecurity user? Well, that can mean many different things, depending on how we track and associate data about users' activities. Which is that there's many ways that users show up on a network according to their interactions with devices, their use of an IP address, their authentication events, and how they connect to subsequent networks and devices, both on their local network and through the internet. And increasingly, as we have mobile devices and cloud-based services, this topic can become very muddled. So essentially, there's a lot of work that needs to be done to prepare for real-time analytics prior to operationalizing the engineering aspects of the solution. And that involves conducting integrated analytics on retrospective data, to conducting forensic analysis of backwards looking cybersecurity data to develop pictures and understandings and models of how users are interacting with a network and devices so that we can create appropriate alerts. And so for this, I can refer to the SAS analytics process, which is a staged process of investigating data, preparing models, and preparing data sets, dealing with data quality, leading up to a staged model and testing of the model, implementation of models, and then the results that come out of models, such as alerts of a cybersecurity incident, which we can then track and analyze and evaluate over time. In a bit more detail, particular to cybersecurity analytics, what we're talking about is a staged process involving first exploration and insights of standing data in batch, so retrospective data, which we use to prepare integrated and formatted data sets, which we then can put forward to prospective models for testing and analysis, and that those models allow us to detect patterns, which we can then put forward and test in operation. Now, in order to stage this, there's an important distinction to be made architecturally when we're managing data between having a batch data repository, a large set of standing data that looks over time, which we can use to conduct exploration and discovery to create and test models, from the operational big data real-time analytics layer. So it's important to note that one is oriented towards storing and analyzing large sets of data from the perspective of the data scientist to develop models. Once those models are developed, they're then instantiated and embedded and influence the types of data that are chosen for implementation in real-time big data engineering solutions, and that there's a relationship between the two. As the results come in from operational analytics, there may be feedback that leads to revision of the models or may give the data scientists indications of something they need to add to the data or improve in the models. So during the process of discovery, data scientists need to apply a very large toolkit of different methods in order to understand and rationalize cybersecurity data and investigate the phenomenon that is going on under the surface inside this data. So one of them, of course, is to understand what are the natural categories. For instance, what are the different types of users that are interacting with the network, devices, and the internet? That is to say, and it's been my experience, that not all users are the same. Some are very technically sophisticated users uh, who are conducting large amounts of transactions through the internet. They're dealing with large sets of data connecting to many different computers. And there's other users who are less sophisticated and may not be on the computer very often. There's essentially a Pareto principle, which I've seen on many different corporate networks across the globe, by which 20% of the users typically generate 80% of the traffic, data, and activities. And it's beneficial if we can understand who these users are and categorize them so that they're marked differently than the users who are using the internet infrequently. Because in each case, it's a lot easier to detect anomalies if users are applied to their peer group, which is to say, a user that doesn't use their computer more than 5 hours a week, typically over the last year, if they're suddenly on 24 hours a day and are downloading terabytes of data, it's clearly an anomaly. Whereas a systems administrator, who may do this as part of their work, should be labeled as such. So we are not bothered when we see that type of activity. So there's an interaction between both the conduct of unsupervised machine learning, which is developing categories and understanding patterns in large sets of data, which allow us to put forward hypothetical categories, which we can operationalize, for instance, in supervised or predictive machine learning. And as we get results, for instance, alerts and anomalies that come from those models, we can then use that to tune and refine our understandings of categories and the data sets that underlie those models. Another example of a data science methodology that is very important for cybersecurity is that of process mining, which is understanding the interactions and transactions that occur over time on networks and with devices, using information about users, IP addresses, and the key entities that are accessing networks. And for this, I can recommend a very good book from a Dutch academic called Process Mining, which gives a lot of examples of the methods that can be used to gain an understanding of processes over time, which can, in the case of cybersecurity, be applied to develop an understanding of the different entities that are interacting in a network and how we might track them and how we might store the appropriate data and analyze the data associated with those entities. Now, once this work is done, you can then use tools such as, for example, SAS's event stream processing to instantiate models, either on an endpoint, for instance, on a device, or to analyze data centrally on a server. Essentially, what we're talking about is that analytics models, such as a machine learning model, is made itself of data. It's an active data vehicle. Using our Lego example, it's one of those very complicated technique Lego sets that may actually have a motor and do very interesting things. But it's itself composed of data, and it requires research and some amount of effort to study the phenomenon that we want to create a model for in order to understand and implement that model. So this brings us to the last topic, which is the organizational aspects of implementing real-time analytic solutions for cybersecurity. We've reviewed how data can be collected and stored, and how we then need to analyze that data in order to create models, which allows us to then create a real-time model for instance, detecting cybersecurity incidents. But that this then needs to be implemented to fit into an organizational process. So for cybersecurity, that often means to fit into a security operations center so that investigators, analysts, and managers can then respond to alerts and follow up on them. And in some cases, they may want to create automated models that will automate those processes. So for this, what essentially we want is, again, a data lake architecture which supports both batch storage for the process of discovery and exploration for data scientists to continually discover potential new events and incidents, and the operational architecture that throughputs rapid, high-speed data through transformation processes using data engineering so that it's then pushed into analytics models that can then assist investigators or in some cases remediate automatically. Now, there's a lot of recent writing and thought that's been put into this, and one of the newer perspectives is that ideally, in order to operationalize these solutions, organizations need to put in place an operationalization analytics lifecycle, which includes a combination of three major functions, which is data ops, model ops, and DevOps. The data ops being associated with data engineering, as we covered at the beginning of this presentation. The model ops covering the data science work that needs to be done, which we covered in the last section. And then the DevOps, which is the management of the deployment of models and the monitoring of those models, and ultimately the exposure of those models to end users in an organization so that they are practical and can be followed up upon. So there's some articles I've put in here, links to more information on this this perspective on operationalizing the analytics lifecycle through these three functions. Essentially, again, using the example of SaaS's event stream processing, a technology such as SaaS ESP supports this, which is that it supports both the investigation, exploration, and discovery, and then the operationalization of models in an analytics lifecycle. Ultimately, when the solutions, the models are deployed, we then want it to fit into a functional architecture in the organization, which is a staged process of high-speed data ingestion, transformation, addressing data quality. That data is then pushed forward to a set of analytical models that allow us to make quick decisions, often automated, which then produces results, in particular alerts concerning incidents on cybersecurity that are then pushed forward to investigators and analysts. So at a high level, what we're talking is a bit of a cyborg architecture, which is the integration of staged technologies that interact with functional roles in the organization focused on cybersecurity. So this brings us to the conclusion, and in summary, what we've covered today has been to address cybersecurity challenges, which is that there is a great hope concerning cybersecurity analytics. However, there are challenges that are created by the volume, velocity, and variety of data that we must manage in order to realize the promise of cybersecurity analytics. And in particular, there are data engineering challenges at a low level, dealing with latency, fault tolerance, scalability, and that over the last decade, the large tech firms such as Google with Google Cloud Platform have addressed many of these issues through very sophisticated cloud-based data engineering mechanisms. And that a great example of this is available through the case study of the New York City Cyber Command department. And that ultimately, when these solutions are deployed, it creates a circular cybersecurity analytics lifecycle, which is a continual improvement of cybersecurity detection models that are then put into production, which improve data engineering, which then go to models, which then feed forward to alerts, which are assessed, and that this is a continual process. We also covered SaaS event stream processing as an example of a type of technology that can help assist and mediate this analytics lifecycle process of both discovery and detection. And we discussed in depth a number of the different perspectives of cybersecurity data science as a discipline in order to create models and analyze data. So with that, I'd like to thank you for your attention and time today. It was a great honor to present to you. Again, I'm sorry I couldn't be in Warsaw myself, and I look forward to interacting with you should you have questions or wish to follow up. I'd be very happy to talk at more length on this and to talk about my research. And with that, dziękuję. I wish you a very fine day and a very fine rest of the conference.